What is up, everybody? Tom McGurl here with another episode of the Learn Rust live stream. On Twitch today, we got Juge Machine in the chat again. Good to have you back. Thank you for stopping by. Today, we're going to be continuing with the exorcism Rust exercises. We started last week. I had a blast. It was like a combination of test-driven development, iteration, so super cool. Definitely doing that again. So we're going to continue that. But first, got to give a shout out. If you're watching on YouTube, thank you. All the subscribers, it's been awesome. I got to give that shout out. Thank you again. For those of you that have been hopping in on Twitch, also greatly appreciated. We had Juge Machine last week. He's going to be lurking here today. That's awesome. And yeah, we're going to continue. We got a little Thanksgiving action going on. We got the turkey here. Some leaves, because it's Thanksgiving in the U.S. on Thursday. So looking forward to that. And I still get to do the stream, right? Thanksgiving never falls on a Tuesday, so we're good. And we'll be on next Tuesday as well, so don't worry. All right, so before things get started, got to do the usual plugs, right? YouTube. If you missed the first episode, we just kicked off exorcism.org. We'll go over briefly what it is again, but not too much of a reintro. If you want to check that out, it's this video right here. We do the first few. It's a little bit of a recap because we did the book, but of course, we're still learning. We're building that muscle memory, and that's really what I'm here to do. I'm here to learn the language. I'm going to use it where I can, build stuff with it when I can. We built an HTTP request with Rust. So we made an HTTP request using the request package, and then we used an API for that I built using Supabase. So check this out as well. The book ended here 7 months ago. Wow. So picked it up, was a little rusty, came back, set up a quick backend as a service, hit it with Rust. Now we're on to Exorcism. As usual, if you want updates for when I go live, and lately maybe a little bit of Halo content, that's just because Halo Infinite came out. I've been playing it, so you might see some tweets about that, but still going to tweet about the Rust. I'll be tweeting when I go live. And of course, I'm going to push the Exorcism stuff out to GitHub. I haven't had a chance to do that yet, but you can just check it out on Exorcism. You can actually just look for my profile, Tom McGurl, and it's all there. But I'll put it here as well, just in case. So, what are we doing? Exorcism, check it out. We're 4.9% through. It's pretty good, not quite 5%. And we're actually, you can see here, there's kind of an outline of the exercises. We did Hello World. We did Lucian's Luscious Lasagna. That was a fun one. We didn't do this one because it's locked. We're going by the syllabus. So you can see we did assembly line, semi-structured logs, health statistics, and then we have two more here that we can actually get to. And the cool thing about those two is they're right here in the syllabus. So we're going to go through the syllabus. We're just going to continue with that. So the next one's the vector macro, then we have destructuring, and then tuples. So that'll be pretty cool. And that's where we'll pick up. We already did functions, enums, floating point, integers, structs, and it's a nice little review from the book, and it's a little different because we can iterate, we could see other folks' solutions, we can go back and improve our solution. But yeah, so let's get started. Again, if you're following along and you don't have Exorcism set up, it's really easy to get set up. I struggled a little bit because I'm running Ubuntu on a Windows machine via Windows Subsystem Linux, but it wasn't too bad. There's instructions for it. So you do that, and then you'll get the Exorcism command line tool. And so what we're going to do is we're going to jump in. Vector macro. We've used it, obviously. It's how we create vectors, right? So we're going to kick it off with a short Fibonacci sequence. Let's build a short Fibonacci sequence. All right. If you're not familiar with the Fibonacci sequence, it's a sequence of numbers where the two previous numbers in the sequence added together make the next number in the sequence. So you have 1, 1. 1 plus 1 is 2. It's the third number. Then you go back and you look at 2 and 1. 2 and 1 is 3. Then the numbers are 1, 1, 2, 3, right? So you look at 2 and 3. The next number is 5. Then you have 1, 1, 2, 3, 5. So you look at 3 and 5. Next number is 8. Then you have 5 and 8, right? Next number is 13. So it builds on it. If you work in a tech company and you do agile, and you are an editor or a software developer or product manager or designer, you might point tickets with the Fibonacci sequence, and that's because it creates a nice scaling jump from what if you go from, let's say, 1 to 2, you know, that's like a nice small measurement. Then you get 3, and as you get bigger, it increases to factor in the level of complexity or the unknown nature. As you start getting that big, things get unknown, so you have to kind of pad it a little bit. So it's a nice system. It's commonly used for that. But of course, it's also fun for exercises. So what are we doing? We're going to initialize empty buffers and list the first 5 numbers or elements of the Fibonacci sequence. Fibonacci sequence is a set of numbers where the next element is the sum of the prior 2. See? We start the sequence at 1, so the first 2 elements are 1 and 1. All right, so we're going to create a buffer of count zeros. So we're just going to create zeros. We can do that using let my buffer create buffer 5. It's going to just create this. And then we're going to list the first 5 elements of the Fibonacci sequence. Create a function that returns the first 5 numbers of the Fibonacci sequence. Its first 5 elements are 1, 1, 2, 3, and 5. So you can see 1 and 1 is 2, 2 plus 1 is 3, 3 plus 2 is 5. All right, so we're just going to copy this, and we're going to go over to our terminal here. Let's make that bigger. And we're going to just do that. It's going to download the exercise, and then I'm just going to go and head right in there. Open it up. And it comes with the tests. So that's how we run it, right? So what we'll do is we'll take a look. This is the file where we're going to put our code, and here are the tests. And so there's one test right now, test. Assert equal, create empty, does a vector new. So create empty should just create an empty vector. And that's the only test that's enabled right now. So we'll run it, make sure it fails, which it should, because of course we haven't coded anything. Cargo test, fails, perfect. So let's go back here and let's implement create empty. So create empty is unimplemented, but of course we know we're just going to do new vec. Oh, we're going to use the macro. So we'll do vec. And that returns a new vector. And so we could also do, of course, vec new like they have in the test. That's also perfect, but we're just going to use the vector. It's a little, or the macro. It's a little bit shorter form. So we'll run cargo test. Our test should pass. Great. So test-driven development. All right, so now we're going to try the next test, which is testing the buffer, test buffer. So there's a create buffer function. So what it expects is to, if you look at the README here, create buffer, if we call it with a length 5, it should create a buffer vector of that same length where each entry is just 0. So basically, we have a usize. We have to create a zeroized buffer of this many bytes, where bytes is the count, right? So how do we do that? Well, we can do, I believe we can do, let's see what we have on vector. I believe we can create a range from 0 to count. And I believe we could iterate over that. Let's see. Let's try something. Oh, I have extra expanded code there. So let's do like for I in 0.5. Let's just try something here. Let mute buffer. So we're going to create a mutable buffer equals vector. And I'm just going to do something silly, but let's see if this actually works. And it would be buffer dot append 0. Let's see. What is this saying? Mismatch types, expected vector 8, found unit type. Ah, because we have to return this, right? So then here we're going to return buffer. Mismatch types, expected mutable reference, found type integer. Ah, because we don't want append, we want dot, we want push. And for count, we want count, not 5. And we're not using I, so we'll just do that. All right, let's see if that works. So what we'll do is we'll comment out our ignore on our test to get it to run. And let's run it, see if it works. This may not be the best way, but it did work. So it did work. I'm sure there's a shorter hand way to do that. And because we have test-driven development, we know this works. So hey, let's refactor it. Let's make it even cooler. Why not, right? So we know this works, our test passes, and if we refactor and we cause an issue and the test fails, well, we know, hey, we just have to go back. That's test-driven development. So let's do a little Googling. Let's see if we can just say create vector from range. See if there's a better way to do it. Create vector from a number range. Oh, and also we should probably search Rust with this, right? Come on. So create vector from range. Let's see if they have any great ideas. We can do collect. So collect. Although we don't want each of the values, we actually just want zeros, right? So let's see. We can try it though. We can mess around and see what happens. So let's search create vector of size. All right, we actually want create vector of size. Vector. Yeah, let's see what else can we have. Create vector from range. How do I generate a vector of random numbers in a range? So this is kind of similar. So again, they're using collect. We can use map. So we can map the range and then collect it all together. We could try that. That's like basically what we're doing with our loop. Yeah, we could try that. So I like that idea. So instead of this for loop, we would basically just create a map. So we could do vector, we create our range. Our range in this case is 0 to count. And it's mappable, right? So we can do map. And then we have our iterator. So we're going to have, we don't really care because we don't actually care about the input of the value. And see here, they're actually, they care about the actual result, but we don't care. So we're just going to do 0. And then if we look at the return type at this point, you'll see why we need to use collect. So now we have a map. It says expected vec8 because of the return type. Expected vec8 found struct map standard ops range use size. So we need to collect it all together as an iterator. And so now we should have collect returns a iterator. So let's see if that in fact works. And we're good. So that's a little bit nicer, right? We don't have to create a mutable buffer. We don't have to push, which is probably inefficient. We can just map over that range. Thanks. And hey, yeah, we Googled it, but we got it right the first time. Then we iterated. I like it. I think this is a cool way to do it. All right, let's see what's next. Fibonacci. So it says create a vector containing the first 5 elements of the Fibonacci sequence. Fibonacci sequence is a list of numbers where the next number is a sum of the previous 2. First 5 elements are 1, 2, 3, or 5. So I guess we only really have to create a vector with that, but we can actually try to also just code the Fibonacci sequence. But let's just see. It looks like they are just doing a test. They assert that it has length 5, right? The first value should be 1. The second value should be 1. And then they assert, let's see, window in fib windows returns an iterator over all contiguous windows of length size. The windows overlap. If the slice is shorter than the size, the iterator returns no values. And then it asserts indices 0 plus 1 equal indice 2. So 1, 1, and 2. So they're not actually checking the full list. So we can actually, let's play around with this because the test isn't a great test. Although actually for window and no, it's doing it for window. Sorry. It's doing it for I'm sorry, I messed that up. it's looking at the windows of the vector. So it's actually, this is really cool actually. So it's testing for windows of size 3. So it's going to get a snapshot of the first 3, and it's checking that this holds true. And then it's going to move to the next window of size 3. So that's really cool. This is an awesome test actually. Look at me. I was going to clown on it, but this is awesome. So first, let's just, because it's actually doing this, we can actually implement the full Fibonacci sequence, and our test will actually test that it works, which I love. So let's do this. First, let's do the dead simple thing to get the test to pass, which is right? It's of length 5. So again, our test is checking that it's of length 5. We could write another test to check more parts of the sequence, but that's really all that's required right now. So let's run the cargo test. All right, so it passed, right? But now what if I added length 6, right? So it's expecting it to have length 6, and it's going to check the entire window. And so it's going to expect 8 at the end. Why is it going to expect 8? Because it's going to expect that 3 plus 5 equals 8, because it's that third window, right? That last window. So let's run cargo test. Let's see it fail. And it tells you here, expected length 5, but it got 6. So if I just add the 8, right, and we run the test again, it should work. Great, it works, but this isn't maintainable, right? I can't just keep adding and doing it manually. So maybe we can actually figure out how to write the Fibonacci sequence. I've done this in the past in interviews. It's never fun because you always have to like resolve it. You don't just like, you could memorize how to do it, but you always have to like talk through it, and that's part of it. It's whatever, it's fun. Let's do that. It's a cool exercise. And I'll probably mess up, but we have our test to verify for us. So basically, we don't have a function that takes a length and computes the Fibonacci sequence for the length, right? So this function, unfortunately, if I go back here, let's go change our test. We're going to keep this function as is for the sake of the test, but we're going to call that to a different function. And so we're going to create a different function here. And it doesn't have to be public. And we're going to call it Fibonacci of length. And it's going to return a vector. And it's going to take a length, which is going to be a size, right? And just to please the thing here, we're just going to do that. And so what we're going to do is we're going to create the Fibonacci sequence. Now we can do it, we're going to be test driving this. So let's do it dead simple, and then we'll try to optimize it. So first off, we can just do a very basic thing, case count. Sorry, I'm used to Elixir. Count, right? If our count is 0, right, we just return vec. If our count is 1, we can simply return vec 1. If our count is 2, we can return vec 2. And the reason I'm doing this is because otherwise we have to handle the scenarios where there's no previous 2 values. Well, if we just handle these values right away, then we don't need to deal with that. Also, what am I doing here? Okay, so if we get a count of 0, just return that. If we get a count of 1, just return that. If we get a count of 2, just return that. And then, again, we're going to get the test to pass. For anything greater, we'll compare the first 2 values. And maybe we can actually use window like they did in the test. Actually do a window, right? We'll see. And so anything else for now, until we compute it, we'll just return an empty vector. So let's try this for the 5. It won't work, right? But what we can do is we can try it. We can write our own test to test that this works for, length to 0 to 2, right? So let's create our own test here, and we'll get rid of it when we submit this. Obviously, we're going, I think, a bit above and beyond for this exercise, but this is fun. Why not? Test Fibonacci for length. And then we're going to do fib.length. We're going to call, let's do fib length, Fibonacci for length. For length 0. We expect that to equal right? And we know this is going to be the case because we wrote it, but just to show that we can add tests ourselves. And we can also, if we don't want to use the macro, we can do, vec new. If it has length 1, we should get 1, and if it has length 2, and yeah, this is a silly test because we know this will work because, of course, it's basically, the test is basically doing the same thing the code does, but it's worth testing anyway. So let's go ahead and run it. And something failed, I think probably because I didn't make it public. Oh, I did make it public. Gotta put that back. And let's see. Oh, cargo test. Cool. All right, so that works. So now let's take a look at our lib. And what do we want to do for when it's not 0, 1, or 2? Well, we want to sum the two previous ones to get the third one. Now, think about this in terms of recursion, right? Because that comes up. You have each value, each third value, or in this case, whatever value you're looking at, right, is the sum of its two previous entries. So if we take a vector of, let's say, length 3, we know that index 0 and 1 are going to be added to create index 2. So we're dealing with index 0, 1, and 2. So we know we have a length 3. And so each of those indices in that length 3 are important, 0, 1, and 2, because 0 and 1 index equal 2. If we have length 4, we know that we're going to be dealing with indices 0, 1, 2, and 3. So we can actually leverage the count to create a range and get those indices. So I'll show you what I'm thinking. So let's do something like that really quick. So here what we can do is we can create a range from 0 to the count, right? And if we actually want to be recursive about this, we can call our function again, right? Create some recursion, which we might do. But what I'm trying to get at is everything in this range is important, and we're going to leverage each of those. And so let's just express it as the way we talk about it, right? So I'll put a comment, index 0 plus index 1 equal index 2. And we see that in the test too, right? That's the formula. So if we have a range, right? And we map over that range, what we're going to get is an index. 0, 1, 2, 3. But what we actually need is to figure out what the value is at that index and add it to the next one, right? So it's actually almost like, if you've ever used a reduce, kind of similar to that, like you're putting the previous output into the current output. So something like fold, if you've used fold, it's similar in Rust. Fold is like reduce. So what that looks like is you would have something like this. Let me pull it up here. Rust fold. This might be useful for us. Oh. So fold will give you the previous value and the next value and let you do something with them. So fold. My D key. There we go. Let's see. Let's go to the docs. Fold, 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 fold. Folds every element into an accumulator by applying an operation. So in our case, we are folding over the previous value, right? And you're adding it to the current value to get the next value, right? 0 plus 1 gives you the next value. Now that's a good way to sum a list, right? Reduce is a great way to sum a list because you're just doing that. But we're not just summing a list. We're dealing with Fibonacci sequence. So we actually need to maintain, right, this array of the sums up to that point. So what are our inputs? Our inputs are the overall array so far, the previous value, and the previous value minus 1, right? Not minus 1, but the previous value before that, the two previous values. We take the sum, pop it onto the array, and return the previous value plus that sum. So what would that look like with a fold? Well, so the way fold works is you have your iterator, you have your initial seed value, and then you have your accumulator. So what if we did this? Let's just see what this looks like. Maybe this isn't the right way, but we have our test, so we can mess with it. We did a fold where our initial value is going to be a tuple. It's going to be an array with 1 and 1, because that's what we're going to start out with, because we know at this point we're at least at 3. So we don't even need to go any. We know we're at 1 and 1 at this point. The other value is the next value, which we don't know necessarily because we want to start off with, well, we know we start off with 2, right? That's the next one. But we want to go until count. So we're folding over. I'm trying to think how the best way to do the initial values. It's probably, I might be overthinking it, but we have the initial value of 1, 1, because we know that's where we're at. We actually don't need to go from 0 because we've already accounted for those. So we actually want to go from, let's see, if it's 0, 1, 2, we actually want to go from 3. And so we'll start with 3 as the initial value because we know that's where we're at. And the next value, well, the sum would be, sorry. We've already solved 0, 1, and 2. So at this point, we're going to solve for 3. And so our initial value is that initial vector, 1, 1. Then we need to keep track of the 2 previous. So in this case, it would be 3, assuming that count is greater than 3, right? Because if you pass a count of, let's say you just passed 3, then your count is from range 3 to 3. You just had the one thing. And so what we'll do is we'll make this one count. No, that doesn't make sense. Let me think about this. 3 is the index. I think I'm thinking about this wrong. We have the array. That makes sense. I'm wondering if fold might not be the right approach, but let me think about it. So you have your array of 1 and 1. We have 3, which would be that value. Yeah, let me think about this. Because I want my list, and then I want, I think I just need the list, and that should be right. Yeah, the index we're going to get. We're going to get what index we're at. Yeah, I think we're good, actually. I think we just need the list as the seed value. Because at the end, we just want to return a list. That's what we want the output to be. Sorry. Okay, so let me just try something else. So we have our list as our seed value, and then what we actually want to do is we want to, sorry, that's the initial value. That's the initial value for the fold. And then we have our function. So our function, I think what we're going to do here is our function is going to give us the accumulator, right? That's everything we have so far. And then the current index. That's what we're at. That's the number we're at. So it'll start at 3, 4, 5. Yeah. And so what we do is, we have our accumulator, we have our index. And then what we need to do is we need to sum if our index in this case is 3, that means the value at 3 is going to be index 2 plus index 1. So we're actually going to do accumulator dot push accumulator index minus 2 plus accumulator index minus 1. That's the formula. If you want to make it in order, like maybe you just do this, right? Make it nicer looking. So let me see if this makes sense. So for 0, we know we're good. 0 is 0. And we're not doing this in a recursive way. We're just going to fold over in a range. Well, maybe we'll try recursion after. But so if it's 0, we're going to just return that. If it's 1, we return that. If it's 2, we return that. If it's anything greater, let's pretend it's 3, just 3. So we should just have a range from 3 to 3. So our index will be this, and it will return this list with 1, because index minus 1, again, index will be 3, so index minus 1 will be 2, which will be this. Oh, actually, we're 0 index, so we want to actually make sure we go from... Yeah, so if our index is going to be 3, then we would look at index 2 and index 1, which isn't enough. So we want to look at actually 2, because that would mean our index starts at 3, our index starts at 2, sorry. And so we look at index 0 and 1. Right? This makes sense, I think. Count from 2 to range, because 2 is... Yeah, this is of length 1. Right, because length 0 is this. Okay. I think that makes sense. Let's think about it though. What's going to happen is if you pass in 3, we're going to have range 2 to 3. That's only one value. Let's see. Why not return accumulator 0 plus accumulator 1, comma, accumulator 1. Instead of just, I see. Do you want the full array? I see what you're saying. So return accumulator 0 plus accumulator 1, comma, accumulator 1. Well, we want the full array because we want a Fibonacci of length blank, right? Let's see. Let's try this. And let's see. What we're going to do is we're going to just call it here instead. So we're going to do Fibonacci of length, and we'll see. We have our tests, so if it fails, it fails. And we want of length 1, 2, 3, 4, 5. Right? So let's see. We have some problems. Mismatch types. Expected struct vector found integer colon 2. 2 vect. Sorry, I didn't do this. There we go. And then here, what is it saying? Mismatch type. Expected vector found unit type. Because we need to return so push, let's see, what does push do? Push is just going to modify mismatch types, expected vector found unit type instead of the unit type output of method push, expected vector because of return type. Method push modifies its receiver in place. Let's see if it has a better thing to use. So maybe we can do append instead. Let's see. What else do we have? We have push. Let's take a look. Rust vector push so push is in place. What is append? Moves all elements of other into self, leaving other empty. So okay, that's for vectors. What if we did insert? Inserts an element at position index within the vector, shifting all elements to the right. Interesting. What about insert? We looked at drain, dedupe, clear. So for insert 1,4, it puts that at the front. Okay, so at position, insert that. Got it. So we could use insert, but it also just modifies. So what if we did, well, we could deal with that. We could just do that. We could just modify it. So what we would do instead is just, I don't know if this is legal looking code. I don't know. What does this say? So now I'm just returning ACC afterward. So ACC's got to be mutable. So what we can do is we can create it as mutable. We can do that here. We could say mute. We could do let's call it sequence. All right. Can I just do that in line? No. Okay, so then we'll make sequence the sequence, and then here let's see, is it cannot borrow as mutable, as is not declared as mutable, cannot borrow as mutable. That's because borrow doesn't need to be mutable, but what if we borrow it here? Mismatch types, expected vector, found reference vector. That's because here we're returning ACC, right? So it expected do you want the full array? Does push return the value? I can't rest. Push does not return the value, so that's why we need to push actually mutates. Although we could probably use append, which is the other option. And so what append did is append takes two vectors, right? You have your vector and you append your second vector. But I'm not sure if it does it in line. Let's see, new. Yeah. Let's see. So let's try this. So right here, I'm just creating the sequence as mutable outside. I'm passing it here. It says mismatch type vector 8, found reference vector to integer. Consider removing the borrow. Okay, so I can get rid of that. And then here we want sequence. Accumulator should be sequence. Consider changing this to be mutable. Yeah. And then I guess we don't need this to be mutable because we made the accumulator mutable. All right, so let's see what this looks like. Looks like we're good. Let me just clean this up and we'll walk through it because I just want to make sure. I wonder if there's a nicer way. Well, we can refactor. If our test pass, we can refactor. We can clean things up. But let's just see what we're doing here. Let's try creating a vector of length 5. Let's go to our tests, make sure our tests are looking correct. let's do another assert here to test this. Let's assert that length 6 equals 1, 1, 2, comma 3, comma 5, comma 8. And let's change that. Let's change this to 7 actually. So length 7 should be this. Why? 1 plus 1 is 2. 2 plus 1 is 3. 3 plus 2 is 5. 5 plus 3 is 8. 8 plus 5 is 13. And we're testing again our Fibonacci of length. And we're passing length 7 because we want 7 entries. Let's test it. All right, so that all works. So we know that this works. If we go to our Fibonacci sequence, so you can see here we're calling it with length 5. We know that this works. So if we even change this, let's change this to length 8. And again, we don't need to change anything else about the test. What we are going to change though is we're going to change this to create a vector of length 8, and everything should still work. Awesome. So our code works. We got a little confusing there, but we used fold, which is kind of cool. So let's go over what we've done. But first, so that we make sure everything passes, is I'm just going to go back and change this back to 5. Now I'm going to keep this test because I want this test here in case we want to refactor further. All right, let's go over it. So what we've done here is, it's a little bit long. We could probably simplify, but let's take a look. If you pass 0 for your count, well, we know the vector is just going to be 0. If you pass 1, we know that you're going to get just 1 back. If you pass 2, we know that you're going to get 1, 1. Now, the reason we did this is because it's kind of hard to compute the first value because there's no 2 seed previous values. So you just kind of got to know when it's 0, it's this, when it's 1, it's this. Same thing with the second one. The second one, you're adding 1 to nothing. So you could say, okay, if there's no value there, use 0. Great. And then, yeah, you'll get 1, but those are kind of like the base cases. So that's why I kept those as what they are. Now, what we do in any other circumstance is we create a sequence, and actually we don't even need this anymore. We can just do this in line here. So we can do some refactoring right away and see if this actually works. And we can run our test to make sure everything's still good. And that's the beauty of test-driven. We can refactor. So what we've done here is we create a range. And the reason we're creating a range to our count is because we need to know the index we're at, the index we want to deal with. And so what we do is I created a range starting with 2. And the reason I created it starting with 2 instead of 3 is because everything is 0 indexed. So you need to subtract 1, right? So even though we want something of length 3, that means the index we're dealing with is 2. Make sense? Okay. So what we're going to do is we're going to use fold. And fold is equivalent to something like reduce in JavaScript. It's a very, very, very powerful function. Super powerful in the functional language, in any functional language, because it allows you to transform something of one type into basically something of any other type by iterating over a list. Because it's so powerful, it's often overused and can create complex code. That's one thing to keep in mind. Sometimes it can make the code a little bit too complex. And maybe we did that here, but we'll see. But it is great for certain things. It's great for performing operations over a list where you want to take the things inside that list and create something new from it. A good example of the use case is summing a list. Reduce is great for summing a list because it can sum the list by just going over the list once, right? You don't need a for loop for that. It's really nice function for that. Creating a map from a list is another great way, right? You have a list and you want to create a map where maybe you take one of the properties from each object in that list, maybe the ID, and you create a map of ID to the object. Reduce is fantastic for that. So really cool for that. And fold is similar, right? So fold is for us basically equivalent for vectors or any iterable. Right now we have a range. And so what we do is we start with our seed value. Our seed value in this case is the list so far. And we know the list so far is this because we're past here, right? So we know the list so far is just 1, 1. Then what we do is we provide a function. And our function takes 2 values. The output of the previous run of the function. If there has not been a previous run of the function, it's the initial value. That's the secret. So the first time this gets called, it's with that initial value. The subsequent times, it's with the output of the previous time. So it's kind of really nice for what we're trying to do with Fibonacci sequence. So we're going to have our it's going to start out with our vector of 1, 1, and then the index that we're looking at. And that index is important because that's how we're going to know where we're looking in that list. So what we do is we push onto that accumulator a new value where the value is accumulator at index -1 plus accumulator at index -2. And we know we're not going to go out of bounds because we know we're past 2, right? Oh, that's cool. So we know that we're past 2, so we're not going to go out of bounds, which is really cool. And that's why we did a case statement here. So this will work. I wish there was a way to just not have to, like, I wish push actually returned a new thing. Maybe there is something that does that I'm just not thinking of. Let's Google it, because that would be a nice, I think that would be a cooler approach. I mean, it's not that big of a deal. It's an extra line, but still it would be cool. Rust push, but return new vector. Let's see. Oh, also, I just realized my window is probably really hard to see, right? For everybody, it's probably super small. Hold on, let me adjust that for you all really quick. This way you can see the full screen. Give me 1 second. I'll just change this over here. It might flash for a second. All right. There we go. Now you can actually see this, and then what I'll do is I'll change this setting. There we go. So that might be a better resolution-wise. Sorry about that. And now you're getting the full picture here. All right, so now what we're gonna do is, yeah, let's see if anything came up out of that search. How can a function append a value to the vector and also return? Why doesn't it return a value? Oh, cool. If you're trying to chain a series of push statements, you can use push all or extend from slice. Let's see if there's something else. How can a function append a value to a vector and also return the value? Let's see. Oh, this case they're dealing with structs. All right, so it looks like, I mean, there's probably a way. We don't have to spend too much time. I don't want to spend too much time on this one exercise, but let's go back. So basically, we push it, and then we return the accumulator. And of course, we have to make the accumulator mutable because we're mutating it, right? That's what push is doing. It's mutating it. Now we could probably create a new, we probably could have created a new vector that was the result of the previous vector plus that extra value. We could probably do that. Let's take a look really quick, just because that might be cool. So that would be create a vector, new vector from 2 vectors rust. Let's see what they say. How to concatenate 2 vectors. Append. So yeah, they're still dealing with mutable vectors here. They're appending to A. In one line. In this case, they're using concat. It takes 2 vectors and concats them. So that could be cool. We could try that. Let's see, rust vector concat. Let's go to our standard library. Let's go concat. All right, let's see. Flatten the slice of T into a single, okay, hello world, concat hello world. Okay. Oh, that's cool. All right, let's try that. Let's try that. Let's see if we can do that. So what we would do then is we would do we would do this. And I think we probably need to concat two lists, right? So we probably need to make a list out of this, even though there's only one item in it. And oh, this is the problem. So this probably needs to be a vector. Yeah, okay, so we just need to make a vector out of this. And what does this say? Expected type vector 8, found array U8 1. Try using converted method 2vec. So that's just because I just need to do this vector macro. And ACC doesn't need to be mutable anymore, is that correct? Yeah, I don't think I need to use mutable value. And this is saying borrow of moved value ACC, value borrowed here after move. Value moved here, move occurs because ACC has type vec, which does not implement the copy trait. Ah, right, okay. So it's actually going to move this value here. So yeah, it's probably gonna be a little more complicated. I think it's probably just similar to, I mean, we can deal with that, but I think it's probably just similar to do this. Pretty straightforward. All right, so let's go ahead and return our, let's just make sure our tests still run first, and then we'll check out what other folks are doing for this one. But what we'll do is we'll put the tests back to what they were so that it doesn't complain or get weird. Just get rid of these ignores. Run our test again, and we're good. And we added some extra coolness to it. So I thought that was pretty cool. And this doesn't need to be public anymore. And again, even though it's not public anymore, our test will still pass because it's not directly importing that in the test. And we are good. So let's go ahead and submit this. Exorcism submit source/librs. All right, it's been submitted successfully. So let's go over and click that. Check it out. Oh, sorry about that. Let's check it out. Ah, hold on. I gotta open it over here. Sorry, Edge. Refresh. There we go. Passed. Your solution looks great. They don't have any recommendations. Great job. Let's take a look at what other folks are doing. Let's look at the one with the highest stars. 8. All right, let's take a look. Ah, this dude. Yeah, he's always putting out some good stuff. Okay, here's some cool stuff. This is nice. You just, instead of, I like this. Check this out. Oh, so this is cool too. Look at that. That's an easier way to create a vector of count. You don't have to iterate over. I like that. Look at that. What a short, cool way to do it. Well, we can iterate. This is cool. So in this case, he's creating a vector with capacity 5, because we only care about 5. And then just starting out with 0 and 1 is the previous and last, which is nice. And so then while result.length, which again is the length of this 5, right, is less than capacity, previous.last equals last, comma, previous plus last, and then pushing that onto result and then returning result. So it only handles 5 in this case, but hey, it could handle more, which is really nice. That's pretty cool. I like that approach. I do like this also, so I want to try that. Let's see if we can do a new iteration of ours. We'll still use our fold, but let's see if we can leverage this previous and last instead of having our match statement. I think it's cool. I know we're spending a lot of time on this, but I feel like it's pretty fun. Hopefully it's fun for you. All right, so let's try that. So first, I definitely want to, and of course we submitted our iterations, so they'll see our iterations. You can see where we started. We got some, check out this, that code. That code looked awesome. We're gonna copy some of that, sweet. But we'll be able to see the iterations, so they'll see where we started, checked out some other solutions, and iterate on ours based on what we see other folks do, which is, it's cool. That's how we're gonna learn. So here, instead of doing this, I didn't realize you could just do vector, right? 0, count. And we run our test. That's pretty awesome. I like that. What a slick way to do it. And then here, we're basically, well, here, the interesting thing is we're able to handle the scenarios where you pass 0, 1, 2, which is kind of nice. So I don't know if I want to change this. I kind of like what we have. One thing we could change, let me think, how could we leverage a previous and next? I mean, I think we could return, let me think. If it's 0, if it's 1. Yeah, I don't know. I kind of like the way this reads out. I don't know if I would change it. So I'm thinking of keeping it this way. Yeah, I'm going to keep it. It's a little different. It has our own little touch on it. So I like that. And it'll handle many more. And we went above and beyond the requirements. You probably don't want to do this if your work just calls for you to create a list of 5, just do it. But I'm like, let's try the Fibonacci sequence. So I like it. So let's submit this iteration because I do like this different version of the create buffer that we saw here, which is awesome. All right, I'm gonna mark this as complete. Yeah, I'll share all my iterations. Why not? Check them out. Tom McGurl, exorcism.org. Just search for Tom McGurl, you'll find it. All right, let's check out more concepts. Destructuring or tuples. Which one is this? Let's see. Low-powered embedded game. This sounds cool. I like games. I think we should do it. Tuples. Tuples are a lightweight way to group a fixed set of arbitrary types of data together. Tuples can have an arbitrary number of elements. You can access the elements by destructuring or numerical position index, so like dot, whatever. All right, let's try it out. Low-powered embedded game. Ooh. Oh. I like it. Let's try it. Let's see what it does. You're working on a game targeting a low-power embedded system and need to write several convenience functions, which will be used by the other parts of the game. All right. One is to calculate the quotient and remainder of a division. Quotient is the output of a division. So div mod takes a dividend and a divisor and returns a tuple. So for example, if you div mod 10 and 3, you divide 10 by 3, you know that it's 3 remainder 1, right? Because it's not, evenly just divisible. So you divide 10 by 3, you get 3, because 3 times 3 is 9, 1 left over, 1. So this is the mod, and that's the value, right? Choose even positioned items from an iterator. Okay, this will be helpful to enable a screen buffer optimization your boss promises. Interesting. Iterators are items which expose the methods defined by the iterator trait. That documentation is fairly extensive because they offer many methods. Here are the most relevant. We've used iterators, right? An iterator is an arbitrary length stream of items. They have an enumerate method, which returns a tuple with the index and the value for each value. They have a filter method, which uses a closure to determine whether to yield an element of the iterator. And they have a map method, which uses a closure to modify elements of the iterator. The closure is that function. It's that function that we pass to our fold. That's all they're talking about there. It's a closure because it encapsulates the values, right? It closes them. Because your function can run any kind of iterator, it uses impl to signify that this is a trait instance instead of a simple item. Likewise, the item T syntax just means that it doesn't matter what kind of item the iterator produces, your function can produce the even elements of any iterator. Okay, all right. So some examples, let's check it out. Even ints. So we pass evens, we pass it 0 to the max that an unsigned 8-bit integer, actually what are they doing here? evens from 0 to that. And it asserts that, oh yeah, so it is. It's creating an iterator, and it's asserting that the next one you have 0, the next evens 2, the next is 4, the next is 5, because it's an iterator, right? It's going to have a next function to give you the next value. Odds from 1 to this. So we're going to have 1, 3, 5, 7. Calculate the Manhattan distance of a position from the origin. For mapping convenience, you have a tuple struct position. All right, so we'll get there. You need to put a method Manhattan on position, which returns the Manhattan distance of that position from the origin. So by position, we mean we're using a tuple like an XY. You could think of it like that. And I believe the Manhattan distance is the exact distance regardless of going negative or positive, if I'm correct. I believe you just absolute value them and sum them. So 3 and 4 would be 7. If it was 3 and negative 4, it would still be 7. If it's negative 3 and negative 4, it would still be 7. I'm pretty sure that's how it works. I forget exactly, but I'm sure it'll be in the tests. So imagine it's the number of blocks you'd have to walk. Yes, it's like displacement, regardless of its position. All right, let's copy that. And we will do, well, we can close this one out. And let's go over here. Let's copy that code. There we go. And let's open up low-powered embedded game. Downloading. Let me zoom in here. It's probably like really microscopic, right? There we go. All right. So here we're going to go to our source, our lib. We have some basic stuff here. And then we have our tests. So for the tests, we have use low power embedded game, divmod. It's pulling that function in. And we're asserting that the divmod 10.3 is 3 and 1. Here we're asserting the power up. That's the name of the function, but it's testing the divmod of 103 is 33 and 1. 3 divided by 10 is 0 and 3. So let's try it. Let's write. So right now this is the only one that's uncommented, so we'll leave it there. And let's write divmod. So it expects a tuple, right? So we can give it a tuple. Dividend, divisor. Let's see what type of that returns, comma. And then we want dividend mod divisor. Nice. Let's try that out. Cargo test. We're good. That one passed. Let's make sure the others still pass. So all I did here is I returned a tuple. The first one is the dividend divided by the divisor, so the division. And this is the mod. That's how you get the remainder. So pretty clear there. And if we look at the tests, let's uncomment some of these. Let's run it now. Still good. We still have some ignore, but all the other ones passed. Now let's go ahead and you can see there the order is non-deterministic, right? So it doesn't necessarily go in the order you think. Good to know. Okay, so now let's do the evens. So if you remember in the README, they mentioned, let me open the README up over here, preview to the side, and let me get Addy away. There we go. So they mentioned we could use, I believe it was Enumerate. Enumerate is going to give us the index and the value. That's what we want. We want Enumerate because we want the index, because we only want to return the even index, right? So check it out. We could use our div mod, but we could just use mod, so we don't need to. All right, so let me close this. So what we're going to do is we're going to go back here. And so for evens, we have our iterator. So we'll just do, look, so here we're just returning empty. That's just to appease the thing there. So what we'll do is we'll do iter dot, and remember we're doing enumerate. And that's going to give us, remember it takes a closure, and it's going to give us the tuple of the index and the value. And so all we're going to do is we're going to say val if, oh, actually we want enumerate. Yeah, so enumerate's going to give us, yeah, okay, so enumerate's going to give us a tuple, so that. And so we want val if, oh, let's take a look really quick. Enumerate. Let's take a look at the docs for that really quick, just because I want to make sure I'm using it right. Enumerate. Iter, rest, enumerate. So enumerate. All right. Not the struct. There we go. There it is. Enumerate. Okay. Creates an iterator which gives you the value. Okay. So, okay. So I messed this up a bit. So enumerate is going to create an iterator which gives you the current iteration count as well as the next value, where I is the current index. Okay. So that's going to give us, it basically gives us the index for each one. Got it. Okay. Got it. So if we enumerate the iterator, if we now map over that, now we should have I comma value, but actually we don't want to map, we want to filter, and we only care about I mod 2 0. Okay, let me show what I'm doing here. We take the iterator, we enumerate it, meaning we create a list of tuples, an iterator of tuples containing the index and the value. We filter that, and we only accept the values for which index mod 2 is 0. It's even, right? So 1 mod 2 is not 0, 2 mod 2 is 0, 3 mod 2, there's a remainder, right? 1, but 4 mod 2 is 0. So this is how you check for evenness. So that should work. Let's test it by going to our tests. Let's check evens. So let's get rid of the ignore here. Get rid of the ignore here. Get rid of the ignore here. What is this one testing? This one's also testing evens. Okay, these are the tests for Manhattan. How are they labeling this? Okay, mod Manhattan. Is this one also inside of mod? Oh, cool. Okay. All right, so we've uncommented all of those. Let's run it. All right, failed. Oh, okay. Expected an iterator. Okay, so let's see. Resolving filter. Expected type parameter t, found tuple u size t. Because we, of course, we still end up with an enumerated list. Got it. Okay, so then I think all we need to do is collect it. What does it say? A value type implementation cannot be built from an iterator over elements of type u size t. The trait from iterator u size t is not implemented for implemented Rust. Okay. Okay, so let's see. What will we do here? Cannot be built from an iterator over elements of type u size t. So we don't really want, so we could do, you know, we could map this again, right? And we can pull out just the value. So what that would look like is map, and again, we're gonna have I comma val, and we could just return val. And now that will just be a list of usize. So we've done a filter. Let me just go ahead and clean this up a little bit. So here we've enumerated it, we've filtered it, and we've mapped it. And you can combine filter, map, and using reduce. Map to only return the second one, exactly. So thank you, Remybox. Good call. Sorry, I did not see your message, but you were right. You had the idea first. So credit to Remybox for this idea. And then we could actually combine our filter and our map. We could use a reduce or fold if we wanted to be slick about it. But I think this is more readable. But we could try them both just for funsies. So cargo test. All right, so that's all good. Now just for fun, let's just see what this would look like as a fold. So I don't know if you noticed this. See how it's expanding all of this stuff? So this is really cool. Basically, this is what Rust Analyzer does. It gives you those inline types. Those actually aren't written in the code. They're inferred by the compiler. And so we're seeing those there. So what's funny is when you see when I commented out, you actually see all the code I wrote. It's not that much. So I just want to see what this would look like as a fold. And so what it would look like as a fold is you'd have your initial value, which would just be an empty iterator. So in this case, it would just be like iterator. Oh, actually it'll be iterator new, right? And then your fold would be what you're folding over. So in our case, we would be doing our accumulator and our next value, or like current. And our current would be the tuple. So we would destructure that. So we could just do ival, not a big deal. And then what we would do is we would filter and reduce in one step. So what we would do is we could do basically let's make this mutable. We would want to do something like acc dot append if it is, sorry, let me just do this just so we have multiple lines. And yeah, this is not going to be as readable. That's why we probably won't. Even though it's one loop, it's still not as nice. And we're doing some mutability and allocating in a certain way, so it's probably not as efficient, but and not as readable, but it's just kind of a fun practice thing. So basically what we would do is we do ACC if I mod 2 does not equal 0, else we would want to return ACC dot push if I mod 2 equals 0, else. And so if it does equal 0, then you would just return ACC dot push val, and then you return ACC. Otherwise, you would just skip it, right? So you would just return ACC. What is this saying? Oh, we probably just do. Let me see what we got here. Our initial, oh, duh. We don't want to start out with an iterator. We want to start out with a vector. My bad. So we have a vector. So let's just test. This should be the same thing, but we'll go back to the filter and the map because it's easier to read. But just for funsies. Oh, vector is not an iterator. Do we want to return an iterator? Interesting. Oh, right. Okay. Yeah, I see. So yeah, I think not worth it. Gonna be too complicated. I think this is more straightforward. I see. So yeah, so because we're dealing with an iterator, not a vector, initializing as a vector wasn't gonna be the way to do it. So I think we're good. Those worked. Now let's talk about Manhattan position. Let's look at the test to get an idea of what we need to do here. So for the Manhattan position, we're looking at distance. So distance from 0 to 0 is 0. Distance from 1 to 1 is 2. Distance from 1 to -1 is 2. -1 and -1 is 2. -1 and 1 is 2. So you can see you're just adding the absolute value. So we're going to ignore the negative. Always ignore the negative. Only positive vibes. Come on. That's like every stream out there, right? Only positive vibes. No, so we're going to ignore the negative, basically. Use the absolute value. So look, 30 and 70, 100. If it was negative 30 and 70, it'd still be 100. Cool? Manhattan distance. All right. Let's do it. So first, let's remove these. And let's run cargo test. They should fail. Great. Now let's actually code this stuff. Oh, what did I do? Okay, let's code this up. Manhattan distance. It takes, we get a position structure. We have these two values in a tuple, and we want to sum them. So we're given self, right? And self is made up of these two values. So what we're going to do, and we need to return a single value, right? The sum. So what we can do is we can say, let's x comma y equal self. Oh. Expected struct position found tuple. Oh. Let position x, y. Now we have the x coordinate and the y coordinate. And what we're going to do is we're going to return x dot absolute plus y dot absolute. I think that's it. I think that's it. Yeah, we're good. What do we do? Easy. We destructured the position, which is self, right? Because this is an implementation block of the position struct. And then we simply took the x and y coordinates, I'm just assuming, positions, right? X and y. We converted them to positive. We just removed the negative. We're using the absolute value. And we just added them together. And that gives us our Manhattan distance. And we're all good. All our tests passed. So I think this looks pretty good. Enumerate, filter map. It's pretty clear what's happening here. This is pretty clear what's happening. You can see this is the division, this is the mod. I'm pretty happy with our code here. So let's submit it. All right, let's go over to the code here, right? Refresh it. I like the Game Boy action. My daughter has a teething toy that looks like the Game Boy. Shout out to Suhan, for my buddy, for getting me that. He might be watching on YouTube. Who knows? All right, so let's see. Mark is complete. No recommendations. Let's take a look at what, there's going to be some young gods in the, with 19 stars. We might have to look at this. Look at this. This is cool. So we did the same thing. Cool. Look at this. Look at that. That's sick. That's super cool. That's way better than ours. Step by. Look at this. Just the swag. Just like new. Yeah, it's better. That's pretty cool though. But hey, that's the cool thing. We found a different way to do it. Rainbox. Okay, that's cheating. Agreed. It's like step by two. I think we did the way they kind of wanted us to do it, to feel. That's why they gave us Enumerate as a hint. Let's check out Step By though. We know what it does now, but come on, it's cheating. Sorry, Step By Iterator. Step by step. Keeps coming up. Step by iter. Let's see. No, I don't want the struct. Step by. It just steps over it. It just steps over it. It's just so easy. But this is the benefit of seeing how other people solve it, but also the docs, right? Creates an iterator starting at the same point, but stepping by the given amount of each. That's awesome. Pretty cool. Pretty cool. Yeah. I think it's pretty cool. We could do that. I'm good with it. I'm gonna pass. I think it's cool, but let's let Steinbro have it. Let's let him have this one. All right, so I'm gonna go back to my solution. Oh wait, we didn't see what else. Anything else? Yeah, that's the same. We did great. What else? We got another cool one. How's this one? Step by, same thing. Oh, they're just using. This is cool, just to illustrate. Instead of destructuring, they're using the index positioning. So also really, really cool way to do it. Remy Box had this great Game Boy. Yeah, I did as well. It was pretty big, and it ate like 4 AA batteries, which was awesome. And I remember driving in the car, and I had to wait till we went under a street light so I could actually see the screen. But it was great. The Game Boy Pocket, though, whew, amazing. All right, so let's go back. Okay, mark it. Yeah, we only did one. All right, let's see. More concepts. Next up is option. I think what we're gonna do is I'm gonna call it here. We'll save these 3 for the next time around. And a little bit early, this way we don't go too far over. And we'll pick up with option next Tuesday. I think that's what we'll do. So I'll get this up on YouTube. I'll post it here. Remember to check out the previous one. If you missed the first chapter, check that out where we went through the first part of the syllabus. But yeah, I think this is a good stopping point. We did pretty good today. I'm pretty happy. We got through vector macro, destructuring tuples. Again, review from what we did in the book. But, you know, it's awesome stuff. Remy Box in the chat said, and once you broke that little tab, you had to use an elastic to keep the battery. Yeah, the little tab that like held the hinge on, the like ridged hinge. Oh my God, it's the worst. And you couldn't wrap the tape around because your buttons were there. So you had to use like, yeah. Or I think I ended up using a epoxy or something to hold that thing on. I didn't break mine though. I actually broke my brother's, so I had to switch and give him mine. But I guess we were lucky enough to have 2. Which is pretty sweet. I don't have it anymore. I got rid of all that stuff and I regret it. I think anyone that got rid of their old game stuff kind of regrets it now. But yeah, so this was fun. We'll continue with it. This just shouted again, exorcism.org. Awesome. You got to check it out. You don't need to be doing Rust. Like that's the beauty. Exorcism has everything. Check it out. What do you want to learn? You want to learn Go? Look at the tracks. You can see I've started some Elm, JavaScript, Clojure, Python, Elixir. I'll probably share some of these as well, but I definitely want to continue with the Rust one. But yeah, anything. Like another cool language, if you're into like the lower level systems programming language, Crystal. That's pretty sweet. Coffeescript, I'm surprised it says new. I don't want to be that person, but like don't do this one. No one's using this anymore. No one uses Coffeescript anymore. All those features are covered in JavaScript. Don't do that one. But other than that, check them out. Erlang, if you use Elixir, you probably have used Erlang, right? Because you can call out to it. It's built on the Erlang VM. Go, a lot of people like Go. Check that out. Haskell, if you're like trying to get like real functional nerdy, Haskell's pretty sweet. If you're getting into Android and you don't want to do React Native, Kotlin's pretty sweet. Lua is cool. You can embed it in programs. Pretty awesome stuff. Yeah, look at all this. Tons of stuff. Check it out. We'll continue the Rust one next week. Again, if you're watching on Twitch, thank you for coming live. This is super cool. Remy Box in the chat. We had Juice Machine in the chat. But if you're watching on YouTube, where I think most folks are, thank you so much for watching. If you want to catch it live, Tuesday nights, 9 p.m. to 11 p.m., You should join. It's fun. It can be really fun. Happy Thanksgiving to those celebrating in the U.S. And I will catch you all next week. All right. Take care. Have a good night.